All right, welcome back. Lesson 2 of Chapter 2, Kinematics Unit. Looking at some displacement time graphs today. We're going to do a little bit more graphing. Hopefully you plotted the data points. This is what's called worksheet number 1 on the or in the homework package that, again, hopefully you printed out online. You plotted a couple sets of data points on a graph, and a displacement or position time graph is another word for it. So this could be a position time graph. Might have been what you saw it called in Science 10 potentially. It looks like we've got a couple of straight lines in there. They're not perfect, but remember that data points in real life will never be perfectly straight. In fact, if I was taking that data as real life data, I'd be thrilled with the straightness or linear nature of those lines. So definitely looks to me like there's sort of two straight lines going on there. So I want you to grab your ruler, if you haven't done this already, and draw a line of best fit through each set of data points. So the green set might look something like that. And then we've got sort of a blue set of data points. And again, there's some wiggle, but split the difference, right? Get some of the points on the high side, some of the points on the low side. I don't know, maybe something like that. So there's what the trend is showing. And now don't worry about the data points at all. It's now the line that we're looking at. That's what we chat about from this point forwards. What I want to do is spend a little bit of time turning this into a story. So like what do those data points actually, or lines, I should say, what do those lines tell us that the object is doing? And it actually tells us a couple of things. We can see that the position is changing as time goes by. So we started at 0 meters, and here we're at 1 meter, and then we're at 2 meters, and then we're at 3 meters. Same with the blue. It's moving further and further away from where it started. So both of these objects are moving. So there's some movement there. And because they're moving into the positive displacements, we could say these things are moving forwards, which means they've got some velocity. And some of you might sort of know where I'm going with this. What does the straight line, remember, don't worry about the wiggly data points, it's the line we're looking at now. What do the straight lines tell you about the velocity? It tells you that the velocity is consistent. It's the same the whole time. We call that in physics constant velocity. So we could say these things are moving forwards with constant velocity. And that's what we want to do with these graphs, is turn them into stories so we could understand if it was a car or somebody walking, what does the movement look like? So these are a couple of objects moving forwards with constant velocity. What can you tell me about the green line, which is steeper, versus the blue line, which isn't so steep? Well, the steeper the line, the faster the object is going. So we've got one object that is simply traveling at a faster constant velocity, and one that's traveling at a slower constant velocity. I won't say fast and slow because it's all relative. We'll just say faster versus slower. So there's some blanks underneath your graph that you can fill in. Here's what we can say. Constant velocity then is a straight line on a displacement time graph. If that data is linear, then we have constant velocity. Steeper slopes mean the thing is moving faster. So they show something like bigger velocities, larger velocity, faster movement. You could put in whatever you want. What if you actually wanted to get the velocity? What if I said, well, how many meters per second of constant velocity do those objects have? Well, then you would simply measure the slope of the line. So the slope of the dt graph is the velocity. Those two things are the same. And remember that slope is rise over run. On our graph, that means the change in displacement. That little triangle is delta, which means change in. It's the change in displacement divided by the change in time. Graph number 2 gave us two other sets of data that looked a little bit different. In this case, those look like curved or nonlinear data sets to me. So go ahead and take a second and draw as smooth a curve in there as you can. It doesn't have to be perfect. So it looks like one object is maybe doing that, and the other object is maybe doing That right there. And let's turn that into a story. What are these objects doing that's maybe the same, but maybe different than the first graph? So here you can see they both started at 0 displacement and moved into the positives. So they're moving still. And they're getting further and further into the positive position or displacements, which means they're moving forwards. But what kind of velocity do they have now? We've got curved lines. And that means it's not constant velocity anymore, it's changing velocity. So they're moving forwards with a changing velocity. And in physics, we call a changing velocity acceleration. So that's what these objects are doing. They're both accelerating. In fact, in physics, we would say they're both accelerating, although some of you might look and say, nah, one of them is accelerating and one of them is decelerating. In physics, we typically like to say positive acceleration versus negative acceleration. And we say that any time you have changing velocity, it's just called acceleration. So we'll get into some nitty-gritty down here below, filling in the blanks. So changing velocity, acceleration. Maybe I'll even put that in there. Is a curved line on a displacement time graph. And if a line is curving up, that means the slope is getting steeper and steeper. And we know that slope is equal to velocity. So that means the velocity is getting bigger and bigger and bigger. We would call that a positive acceleration. Or, I think a nice thing to say would be that it's speeding up. And a nice reason that we can talk about that as speeding up is that speeding up is an upward curve. This is like half of a smile, right? That's an upward curve. So any part of an upward curve like this on a graph, even this section right here, the line's trying to curve upwards. Any part of an upward curve is speeding up, which we would call positive acceleration. Contrast that with something sloping downwards. That means the slope is becoming flatter and flatter. The velocity is becoming less and less. That's a negative acceleration. That's what we would call it in physics. I also like to call it slowing down. And that's because it's a downward curve. Any part of an unhappy face, any part of that shape, is the line trying to curve down, so it's slowing down. You have to be a little bit careful. Sometimes people will call this deceleration, although that's maybe not the best word to use because when things go backwards, it gets a little bit dicey. So I'll put that as be a bit careful. But you could say it's decelerating, it's slowing down, especially if it's moving forwards. That's fair game. So thinking about linear data sets, straight lines, finding slope of that's easy. We've already done it a whole bunch in this course. You've done it a bunch of times in math. You simply calculate rise over run. You could ballpark it for this green line by looking at sort of 1 second and saying, what's the slope there? Well, in 1 second, it rises 1.2 meters. Rise over run, 1.2 divided by 1. The velocity is about 1.2 meters per second, right? Ish, because again, I can't really see that graph with too much detail. But you could do a little slope triangle, you could measure the slope, done. The trick is, what do you do with curved lines? What do we do with lines like that? It doesn't really make sense to talk about the slope of the line because the slope of the line is changing all the time. So what we do is we don't just talk about velocity for curved lines, we talk about two special types of velocity. The first one is an average velocity, which is the slope of a line that joins 2 points on a curved dt graph. So we're going to join 2 spots on that curve, one of the curved lines. We're going to find the slope of that, and then that's going to be our average velocity. It does occur over a time interval though, right? There has to be like a starting time and an end time. So let's try finding the average velocity of object 4. That's the line that's curving upwards on worksheet number 1. Let's figure out the average velocity between 1 and 3 seconds. So if you go back to your curved line on worksheet 1, we want to draw a line between 1 second and 3 seconds. So on your line, put a couple dots, one of them at 1 second, one of them at 3 seconds. Grab yourself a ruler. Oop, we've done a little scaling there. Grab yourself a ruler, draw a straight line in between them. And now we're going to turn that into a slope triangle. So there you go. Show your rise, show your run. That scaling piece, we did have to figure out sort of what each box is worth. So you can see here, you can't just count boxes. This would be like 1.2. So every box on the time axis is worth 0.2. That's easy. Every box on the d-axis is also going to be worth a 0.2. So you'll need to know that so you can figure out sort of where your big and small values are. If I use that scale and I figure out my delta D's and delta T's, it might look something like that. Delta T is 3 minus 1. And my delta D looks like about 2.1 minus something a little bit bigger than 0.2. So I'm going to call it 0.25. M for meters. Yours might be slightly different. Don't worry about it. Go with your values. As long as we're close, that's good enough. Now if I take my rise over run calculation with those values, I end up with something like 2 or 3 sig figs plus units on all final answers, don't forget. Something like 0.925 meters per second. And yours might not be exactly that, but again, as long as you're close. Mine is not the answer, it is simply one answer. So if we're sort of, I'd say 1-ish meters per second, then you're A-okay. So there's your average velocity from 1 to 3 seconds. The other kind of velocity is called an instantaneous velocity. And that is the slope of a single line, which we call a tangent line. And we draw it at only one point on the graph. The instantaneous velocity occurs at one time because it's the velocity at one instant. So if you're speeding on a road and a police officer uses a radar gun to capture your speed, that police officer is going to be sort of tracing your car, and then maybe she hits the trigger on the gun and it locks in a velocity. That was how fast you were going right there, right at one instant. And then the number's locked on the screen. That's an instantaneous velocity. So maybe you were going faster before and slower after, but that police officer now has your velocity at that one instant. They have an instantaneous velocity that they may or may not use to give you a ticket. So here's what I want us to do. I think actually on yours it's at 1.5 on your piece of paper, so we'll change this. Let's determine the instantaneous velocity of object 3, that's the downward curve, at 1.5 seconds. So here's the graph. I believe for us, I'm going to have to change this a little bit. I'll do it with you in real time. Put a little dot on your curve at 1.5 seconds, which is going to be right there. Now what we're trying to do with a tangent line is show the slope of that curve at just that one spot. So here's what I like to do. I like to draw just a little line over top and say, hey, there's the slope of my curve right at 1.5 seconds. But I can't really slope triangle some tiny little line like that. So what I do is I grab my ruler and I extend it out in either direction. That's a tangent line. And make it huge so that you've got lots of potential spots for a slope triangle. Now notice the spacing between your tangent line and your curve. You're looking for it to be kind of sort of the same on both sides. So that'd be a nice tangent line. And now you're looking for a couple of spots to draw a slope triangle. So go ahead and pick a couple of spots. Maybe you get some nice spots, maybe not. Make it nice and big. That is definitely something that we want to do. So I'm going to fudge some numbers. I'll pause the video and just put some numbers on there. But maybe I go between those two spots. So sketch yourself a little slope triangle out of that. Find your delta D's and your delta T's. And then the slope of that slope triangle will be your instantaneous velocity. So I'm going to pause the video for 2 seconds. You're going to see a bunch of numbers show up on there. So I think those are the values for mine. I figured out my big minus small for the time axis and for the displacement axis. And now you can go and show this on your page. The instantaneous velocity then is going to be equal to rise, which is 4.4 minus 1 meter, divided by the run, which for me was 2.4 minus 0.2. Go with your own values though, right? Don't worry about mine. As long as we're close-ish. Make sure you use brackets. 4.4 minus 1 divided by 2.4 minus 0.2. I get 1.55 if it's 3 sig figs. So again, that's not the answer. It's just one answer. I'd say as long as you're close to something like 1.5 meters per second, then that's going to work. So that's a tangent line. Maybe we should actually label that. So that was a tan line or tangent line. The other line, by the way, if you want to put a name on it, when you join 2 points on a curved line, we can see ours underneath here, that's called a secant line. Not that you have to memorize that, but just in case you hear somebody talk about it. So I'm going to skip ahead in my numbers here. This is the sort of last little bit of today's lesson, but I'm going to hit it first before, well, I shouldn't say first. I'm going to hit it before something else. What I want to go over is how to plot data from ticker tape information. So from measuring dots on pieces of paper. What I'll get you to do here is this displacement versus time graph is all ready for you to roll. Can I get you to take a second and plot your data points for time and displacement, the first 2 rows, and see what kind of shape you get for that graph. So there's my data points plotted. To me, that looks a lot like a curved line, like an object that has some acceleration. So you can go ahead and you can draw in as smooth a curve as you can, just because we want to show people what the object's doing. We don't play connect the dots because it's not moving all sort of herky-jerky. It's moving in a nice smooth fashion. Now, that's the first graph, time and displacement, so we got that done. Now it wants us to do a velocity time graph. And there was a problem, and remember that problem was, how do you slope a curved line, right? How do you turn that one curve into some velocity time graph? And I guess you could, if you wanted to, this would be tedious, do a whole bunch of little average slopes in there. Draw a whole bunch of secant lines and a whole bunch of slope triangles, but that takes a long time. So I'm going to offer you an equation that will turn that displacement time data into velocity time data, and it does it very, very nicely. So here's how you calculate velocity. Maybe we can jam it in on your page towards the bottom. To find velocity, the calculation looks like this. d2 minus d1 divided by the change in time. So what the heck do I mean by that? Well, let's pick a box. Let's look at this one. Right there. When I say d2, I'm simply talking about the number that is on the right-hand side. You can see this box is straddling 2 different displacement values. So d2 is not the bigger number necessarily, it's just the number on the right, minus d1, which is the number on the left. So it's 4 minus 2.25. So let's put an example in there. 4 minus 2.25 divided by, now it's talking about delta t. And you're going to look and you're going to see that box and you're going to go, oh, weird. It's kind of touching like 1.5 seconds and 2 seconds. So do I divide by 1.5 or do I divide by 2? And that's kind of a trick question. You actually don't divide by either of those. You divide by the change in time. So what's the difference between 1.5 and 2 seconds? Well, it's half of a second. And you can see that we are just ticking up by half of a second every time. So every calculation we do, and we're going to do all those ones up there, is going to be division, in this case, by 0.5. And if you throw that into your calculator, again, be a little bit careful with brackets. Divided by 0.5, you're going to get 3.5. So that box right there, get rid of those arrows, was 3.5. So go ahead, take a moment, try the rest of the calculations for that row. So there they are. Notice there's a nice pattern there. This data's been pre-cooked like a hot dog so nobody gets sick. Sorry, bad physics jokes. So there's how you calculate your velocities. Now we want to plot those velocities on the graph. And the next question might be, okay, Heinrich, where do we put these data points? Like this 0.5 meters per second, does it go with 0 seconds or does it go with 0.5 seconds? Because it's kind of straddling like two different values. And the answer is that it actually doesn't go with either of those. What we want to do is we want to plot the velocity row. Notice it's staggered. It's like in between the two boxes. We're actually going to plot these on the in-between times. So we're going to plot, for example, at 0.25 seconds. And then 1.5 goes between 0.5 and 1.0, which is 0.75. Oops. 0.75 seconds. And then the 2.5 is going to go in between there, which is 1.25, and so on. So when we go to plot this velocity time graph, we plot on, I'll put it in quotes here, the in-between times. So it's not actually on the times that are sort of labeled on the axis. It's going to be the in-betweens. And I'm not going to put all the arrows in, but something like that. So take a moment, try that out, see what you get for a line. So I plotted my data points, looking awfully linear to me. Got those points on the in-between times. That is a straight line, so you can grab your ruler. Might be perfectly straight, actually, so you can play connect the dots, which is always fun. We have an object looking like that. So acceleration on the displacement time graph was an upward curve. And now we've got that positive acceleration on a velocity time graph being just an angled straight line. So it's got some constant acceleration. Check out the next video. I'm going to stop this one here because it's getting kind of long. Check out the next video for, oh, I didn't fill in that number, 3.5, sorry. It's going to be a really short one. It's going to be talking about converting between graphs, not using this equation. And I'm going to do the homework with you, which is worksheet 2. So make sure you watch, I guess this is lesson 2. Watch the video for lesson 2B, which will be sitting on the website. We will chat about this lesson a little bit more. Talk soon.